Right now, above your head, there is something you have never felt move. Space itself. It looks empty. It looks still. But space is not nothing. It has a shape. And that shape can bend and stretch and shake the way a drum skin shakes, the way a sheet of rubber gives way under weight. In the year 2015, for the first time in human history, we caught it moving. Two black holes, each one heavier than 30 suns, collided over 1 billion years ago, far across the universe. The crash sent out a ripple, a wave in space itself, and that wave crossed the entire universe just to reach us. By the time it arrived on Earth, it had stretched a tunnel 4 kilometers long by less than the width of a single proton. We built a machine sensitive enough to catch that. And once you can measure how much space bends, a strange, almost forbidden question opens up. If space can bend, does that mean space has a limit? Does that mean if you pushed hard enough, space could snap, tear, break apart, the way glass shatters, the way a rope gives out under too much weight? Tonight, we are going to ask that question properly, using real physics, real numbers, the same tools engineers use to test steel and diamonds and the wings of aircraft. So get comfortable, settle in. And if this is your first night with us, hit like and subscribe, because by the end of tonight, you will know exactly how close the universe has ever come to breaking itself. Prepared yourself, and let's slowly begin. Part 1. The sound made of proof. To understand what it would even mean for space to break, you first have to understand what it means for space to bend. And for that, we need to go back to a night in September of 2015 in the quiet control rooms of two facilities thousands of kilometers apart, one in Louisiana, one in Washington State. Nothing about that night looked dramatic. There were no sirens, no flashing lights, no sense of occasion, just rows of screens, humming servers, and a handful of scientists doing what scientists do at 3 a.m, watching numbers that almost never change. And then, for a fraction of a second, they did. A signal swept upward through the data, rising in pitch, rising in strength, lasting about 0.2 of a second before it vanished. If you converted it into sound, and scientists did, it makes a soft rising chirp, almost like a bird call slowed down and dropped into the bass register. That chirp was not a recording of a black hole. It was not an image. It was something stranger. It was space itself, moving, to understand what had just been detected. You have to picture something most people never think about. Space, the actual fabric that holds the distance between you and the wall behind you, between the Earth and the Moon, between one galaxy and the next, is not fixed. It is not a rigid backdrop painted behind the universe like the set of a play. It has structure. It has give. And under the right conditions, it can ripple the way the surface of a pond ripples when you drop a stone into it. Here is the picture physicists use to think about this. Imagine a flat slice of space, and imagine scattering a ring of small, weightless test masses across it, evenly spaced, like the numbers around a clock face. Now imagine a gravitational wave, a ripple in space-time itself, passing directly through that slice, moving perpendicular to it, straight through the center of the clock. As the wave passes, the ring does not stay a perfect circle. It stretches gently into an oval along one direction while squeezing slightly along the other. Then, as the wave continues, the stretching and squeezing reverse. The oval flips its orientation, stretching where it had squeezed, squeezing where it had stretched. This happens again and again and again in a smooth repeating rhythm for as long as the wave keeps passing through. If you were floating at the center of that ring, you would feel nothing. No wind, no pressure, no sensation of any kind. And yet the distances between the masses around you would be changing in a precise, measurable, rhythmic way. That is the strange, quiet violence of a gravitational wave. It does not push matter. It does not blow through space like wind. It changes the very meaning of distance as it passes. Physicists have a way of putting a number on this distortion. Picture the top mass in that ring and track how far it moves away from its resting position as the wave passes through. If you plotted that motion over time, you would see a smooth, oscillating wave, rising and falling in a steady rhythm. Now take the size of that displacement and compare it to the original radius of the ring. That ratio, the amount of stretching divided by the original size, is called the strain. Physicists usually write it with the letter H. If H is large, the stretching is dramatic and easy to see. If H is small, the distortion is close to invisible, buried in a haystack of ordinary vibration and noise. And here is the astonishing part. This exact same idea, this exact same ratio, is what LIGO was built to measure. Instead of a ring of floating test masses, LIGO uses two long vacuum tunnels, arranged in an L shape, each one about 4 kilometers long. A single laser beam is split in two, sent down each tunnel, bounced off mirrors at the far end, and brought back together at the corner where they started. If both tunnels are exactly the same length, the two halves of the laser beam recombine in a fixed, predictable pattern, and the detector sits in near total darkness. But if a gravitational wave passes through the detector, one arm stretches while the other one is squeezed, and then, a fraction of a second later, the process reverses. That tiny difference in arm length shifts the two laser beams out of perfect alignment, letting a flicker of light leak through where there should be none. That flicker of light was the proof. That flicker of light is a gravitational wave being caught, quite literally, in the act of moving the fabric of the universe. Now, here is the number that should genuinely stop you for a moment. For that very first detection in September of 2015, the peak strain measured on Earth after a signal that had been travelling for more than 1 billion years, crossing galaxies, crossing epochs of cosmic history, arriving finally at a set of mirrors in the American countryside, was roughly 1 part in 10, followed by 21 zeros. That number is almost too small to hold in your mind, so let's turn it into something physical. Each arm of the LIGO detector is about 4,000 meters long. If you take that strain and multiply it by the length of the arm, you get the actual physical change in length caused by the wave. The answer comes out to about 4 times 10 to the minus 18 meters. To put that in perspective, a single proton, one of the smallest, most fundamental building blocks of matter, has a diameter of roughly 1 times 10 to the minus 15 meters. The change LIGO detected was thousands of times smaller than that. Smaller than a proton. Smaller in a very real sense than anything that should be measurable by any instrument built by human hands, and yet we measured it. 2 black holes, more massive than our sun many times over, spiraling into each other faster and faster until they merged into one, released more energy in that final fraction of a second than every star in the observable universe combined, radiated outward as light. Almost none of that energy came out as light at all. It came out as ripples in space-time itself, and those ripples crossed more than 1 billion light years of empty space, growing fainter and fainter until they arrived at Earth and stretched a steel and glass instrument by less than the width of a single subatomic particle. And we caught it. That detection confirmed something Albert Einstein had predicted almost reluctantly in 1916, nearly 100 years earlier, buried inside the mathematics of general relativity. Einstein himself was not fully convinced gravitational waves would ever be detectable. He suspected the effect might simply be too small, too delicate, too easily lost in the noise of an imperfect universe to ever be measured by anything real. He was right about how small the effect would be. He simply underestimated what human ingenuity a century later would be capable of building. But confirming the wave itself was never really the end of the story. It was the beginning of a much stranger one. Because once you can measure how much space bends under the pressure of a passing wave, a door opens onto a question that sounds almost like science fiction, but is entirely serious physics. If space can be stretched, does that mean space has a stiffness, a resistance, a structural property, the same way steel resists bending, or rubber resists stretching, or diamond resists nearly everything at all? And if space has a stiffness, then somewhere, in principle, it must also have a breaking point. That is the question we are going to spend the rest of tonight chasing, all the way down to the smallest possible scale the laws of physics allow us to describe. Part 2. The question nobody expected to be serious. There is a particular kind of question that sounds, on its surface, almost childish. The kind of question a curious 10-year-old might ask and immediately be told to stop being silly. How stiff is space? Not how strong is gravity, not how fast does light travel, but literally. If you tried to stretch empty space the way you might stretch a rubber band, how hard would it push back? For most of the history of physics, nobody asked that question seriously, because there was no way to answer it. You cannot walk into a laboratory, take hold of a piece of empty space, and pull. There is no handle. There is no material to grip. Space does not sit on a table waiting to be tested the way a steel bar does. And so, for 100 years after Einstein published general relativity, the question of the stiffness of space-time remained at best a strange footnote, a thought experiment with no obvious way forward. Then, in 2018, at a public lecture honouring the memory of physicist Frederick Reynes, the theoretical physicist Kip Thorne stood in front of an audience and spoke about gravitational waves, about LIGO, about everything that detection in 2015 had made possible. And at the end of his talk, during the question period, someone in the audience raised their hand and asked him directly, "What is the Young's modulus of space-time?" It is worth sitting with that question for a moment, because it is not a joke, and it is not nonsense. A Young's modulus is a real, well-defined physical quantity. Engineers use it every single day to describe how stiff a material is, whether they are designing an aircraft wing, a suspension bridge, or the frame of a building. Asking for the Young's modulus of space-time is asking whether the fabric of the universe itself can be described using the exact same mathematics we use to describe steel. Thorne did not answer the question himself. Instead, he turned it over to a colleague sitting in the audience that night, the physicist Rainer Weiss. Weiss, along with Thorne and the physicist Barry Barish, would go on to share the 2017 Nobel Prize in Physics for their decades of work building LIGO and turning gravitational wave astronomy from a theoretical dream into a working science. If anyone alive was qualified to answer that question, it was him. Weiss explained that there is no single fixed answer. The effective stiffness of space-time depends on the frequency of the gravitational wave passing through it, the same way the effective stiffness of a drum skin depends on how fast you are tapping it. But at the frequencies LIGO actually detected, around 100 cycles per second, Weiss gave a number. Space, he said, behaves as though it were roughly 10 to the 20th power times stiffer than steel. 10 to the 20th power. That is a 1 followed by 20 zeros. To grasp how enormous that number actually is, imagine lining up 100 billion pieces of steel, end to end, each one contributing its own resistance to being stretched, and somehow combining all of that resistance into a single sheet. That, roughly, is the kind of stiffness we are talking about. Not a little stiffer than steel, not twice as stiff, 20 orders of magnitude stiffer. That number sat in the room that night as a kind of beautiful curiosity, a party trick pulled from decades of hard-won expertise. But where does a number like that actually come from? How do you take a laser detector, a chirp of sound lasting 0.2 of a second, and a wave that stretched space by less than the width of a proton, and turn all of that into something you can compare directly to a bar of steel? To understand that, we first need to understand how physicists measure stiffness in the first place, using nothing more exotic than a rod, a clamp, and a pulling force. Picture a steel rod, clamped firmly at one end. You take hold of the other end and pull, gently, with some measured force. The rod stretches, just slightly. Pull twice as hard, and for small deformations, it stretches almost exactly twice as far. Pull 3 times as hard, and it stretches 3 times as far. This simple, elegant relationship, first described in the 17th century, is known as Hooke's law, and it holds true for an enormous range of materials, provided you do not pull hard enough to permanently deform or break them. Now suppose someone tells you they pulled on a rod with a force of 1,000 newtons. Is that a large force or a small one? The honest answer is, it depends. If that force is spread across a rod with a cross-sectional area of 1 full square meter, it is spread thin, diluted across a wide surface. But if the exact same force is concentrated into a rod with a cross-section of just 1 square millimeter, that force is compressed into an area 1,000,000 times smaller, and the effect on the material is dramatically more intense. What actually matters, physicists realized, is not the raw force itself, but the force divided by the area it acts upon. This quantity is called stress, and it is measured in units of newtons per square meter, a unit more commonly known as the Pascal. Now imagine 2 rods made from completely different materials of completely different lengths. If you pull on both and each one stretches by exactly 1 millimeter, has each material responded the same way? Of course not. A short, thick rod stretching by 1 millimeter has deformed far more proportionally than a long, thin rod stretching by the same amount. What matters is not the raw change in length, but the change relative to the original length. This ratio, the change in length divided by the original length, is called strain. And notice, strain has no units at all. It is a pure ratio, a fraction, which means it lets you compare the deformation of completely different materials, of completely different sizes, on exactly equal footing. Here is where the elegance of the whole system reveals itself. For most materials, across a wide range of applied forces, stress and strain are directly proportional to one another. Double the stress, and you double the strain. Halve the stress, and you halve the strain. If you were to plot stress against strain on a graph, you would get a straight line, and the steepness of that line, its gradient, is what physicists call the Young's modulus of the material. A high Young's modulus means the material barely deforms even under enormous stress. Diamond, one of the stiffest naturally occurring materials on Earth, has a Young's modulus of roughly 10 to the 12th power pascals. Steel comes in a bit lower, at around 10 to the 11th power pascals. Soft rubber, by contrast, deforms easily under even gentle pressure, with a Young's modulus of only around 10 to the 6th power pascals, 1,000,000 times softer than steel. So now we have a real, precise, well-tested way of quantifying stiffness. But LIGO never pulled on space with a known calibrated force the way an engineer pulls on a steel rod in a laboratory testing rig. LIGO simply watched space stretch and squeeze on its own, driven by a wave that had been traveling unassisted for over 1 billion years. There was no clamp, there was no measured pulling force. There was only a strain, a tiny fractional change in length, arriving unannounced in the dead of night. So how do you get from that lonely, passive measurement, a strain with no accompanying force, all the way to a genuine estimate of stiffness? The answer, as it turns out, is not force at all. The answer is energy. And to understand how energy bridges that gap, we need to think carefully about what actually happens physically when any elastic material is stretched, and what that stretching costs. Part 3. What it costs to stretch anything at all. Whenever you stretch an elastic material, you are doing work, not in the casual sense of exerting effort, but in the precise physical sense that physics gives to that word. Work is force applied over a distance, and whenever you apply a force to stretch something, and that something moves in response, energy is being transferred into it. That energy does not vanish. It gets stored, held inside the material itself, in the same way a drawn bowstring stores the energy of the archer's pull, ready to be released the instant the string is let go. Picture, once again, our steel rod, clamped at one end. This time, instead of applying a single fixed force, imagine gradually increasing the pulling force from 0, smoothly, steadily, until the rod has stretched by some small amount. If you plotted the force against the extension as you did this, you would get a straight line, exactly as before, because the rod is behaving elastically. And here is the elegant part. The total work done in stretching the rod, all the energy you have poured into it through your steady pulling, is equal to the area underneath that force extension line. Because the line is straight, the shape underneath it is a simple triangle, and the area of a triangle is 1/2 its base multiplied by its height. In this case, that translates into 1/2 the final force multiplied by the final extension. That quantity, 1/2 force times extension, is the elastic potential energy stored inside the rod. It is the same kind of energy stored in a compressed spring, or a bent diving board, or the taut string of a bow. But a raw energy value on its own is not especially useful for comparing different materials or different situations. What we really want is energy density, the amount of energy stored per unit volume of the material, because that lets us compare a tiny sliver of steel to an enormous girder on completely equal terms. The volume of our rod is simply its cross-sectional area multiplied by its length. And if we divide our expression for the stored energy by that volume and rearrange the resulting expression carefully, something beautiful happens. Two familiar quantities emerge from inside the algebra, quantities we have already met. The force divided by the area is the stress. The extension divided by the original length is the strain. And the energy density collapses down into an astonishingly simple form, 1/2 stress multiplied by strain. And because we already know that stress equals the Young's modulus multiplied by strain, we can substitute that relationship indirectly, and the energy density simplifies even further into 1/2 the Young's modulus multiplied by strain squared. This is one of the most quietly important equations in all of materials science, and it is worth sitting with for a moment before we move on, because everything that follows tonight depends on it. It tells you that for any given amount of strain, a stiffer material, one with a higher Young's modulus, stores dramatically more energy. Squeeze a piece of rubber and a piece of diamond by exactly the same fractional amount, and the diamond, being vastly stiffer, will have vastly more energy locked inside it. Stiffness, in this sense, is really a statement about how much energy a material is willing to hoard for a given amount of deformation. Now here is the conceptual leap that turns this from ordinary materials science into something genuinely strange. We are going to take this exact equation, this relationship between energy density, stiffness, and strain, and we are going to apply it to empty space itself. To be absolutely clear about what we are doing and what we are not doing, we are not claiming that spacetime is literally made of atoms or crystal lattices or chemical bonds the way steel or rubber or diamond actually are. General relativity contains no such microscopic structure. Space, as far as Einstein's equations are concerned, is a smooth, continuous geometric object, not a physical substance built from smaller building blocks. What we are doing instead is asking a purely hypothetical but mathematically precise question. If space-time behaved as though it were an elastic material, storing and releasing energy in exactly the way steel or rubber does, then what value of stiffness, what effective Young's modulus, would it need to have in order to produce the exact strain we measured at LIGO? This is not a claim about the deep nature of reality. It is a way of taking a real, measured number, the strain LIGO detected, and translating it into language borrowed from an entirely different branch of physics, so that we have some intuitive way of grasping just how extreme that measurement actually was. To make this translation work, we need one more ingredient. We need to know how much energy the gravitational wave itself was actually carrying as it passed through the detector. If we can estimate that energy density independently using the physics of gravitational waves rather than the physics of elastic rods, then we can set the two expressions equal to each other and solve for the effective stiffness of space. So let's build that independent estimate from the ground up. As a gravitational wave passes through a region of space, the strain does not sit at some fixed value. It oscillates, rising and falling in a smooth, repeating rhythm, exactly like the tide coming in and out, or a pendulum swinging back and forth. We can describe this mathematically by writing the strain as a function of time, oscillating sinusoidally with some peak strain value and some frequency, the number of complete oscillations the wave completes every second. Now, intuitively, you might guess that the energy carried by the wave should depend on how large that peak strain is. A wave that stretches space by a large amount should carry more energy than a wave that stretches it by only a tiny amount. That intuition is correct, but it is not the whole story. The energy also depends on how quickly the strain is changing, on the rate at which space is going from stretched to squeezed and back again. A gentle, slow oscillation carries less energy than a rapid, frantic one, even if both reach the exact same peak strain. This rate of change is simply the gradient of the strain over time, the steepness of the curve at any given moment. But there is a subtlety here that deserves attention. During part of each oscillation, the strain is increasing and the gradient is positive. During the other part, the strain is decreasing and the gradient is negative. Physically, though, energy does not care about the sign of that change. Whether space is stretching or squeezing, energy is still flowing through it. This tells us that the energy carried by the wave should depend not on the rate of change itself, but on the square of that rate, a quantity that is always positive, regardless of which direction the oscillation happens to be moving in at that instant. And this is exactly what the full mathematics of general relativity confirms once you work through it properly. If you take the strain, oscillating sinusoidally with some peak value and some frequency, and differentiate it with respect to time to find its rate of change, and then square that result, you find that the outcome scales with the frequency squared, multiplied by the peak strain squared. In other words, ignoring the fine details of the oscillation itself. The flux of energy carried by a gravitational wave scales as frequency squared multiplied by peak strain squared. This tells us something intuitively satisfying. You can increase the energy a gravitational wave carries in two independent ways. You can increase the frequency, making space stretch and squeeze more rapidly, more urgently. Or you can increase the peak strain, making the stretching and squeezing itself more dramatic. Double the frequency while keeping the strain fixed, and the energy carried by the wave quadruples. This is not a small effect. It is a steep, unforgiving dependence, and it is going to matter enormously once we start asking what happens at truly extreme frequencies. Far beyond anything LIGO has ever detected. But right now, we have only established how the energy scales, not its actual numerical value, and there is still a mismatch sitting quietly underneath everything we have done so far. A mismatch in units that we cannot ignore. To resolve it, we are going to have to reach for two of the most fundamental constants in all of physics: the speed of light and Newton's gravitational constant, and discover, almost like a key sliding into a lock, that they fit the missing piece of this puzzle exactly. Part 4. The constants that hold the key. Physics has a peculiar kind of honesty built into it, one that mathematics enforces whether you want it to or not. Every physical equation has to balance, not just in its numbers, but in its units. You cannot set an energy equal to a length or a force equal to a speed. If the units on either side of an equation do not match, something in your reasoning has gone wrong, no matter how elegant the algebra looks on paper. And that is exactly the wall we ran into at the end of the last part. We had established that the energy flux of a gravitational wave, the amount of energy passing through 1 square meter every second, scales with the frequency of the wave squared, multiplied by the peak strain squared. But if you check the units on each side of that relationship, they do not match. Energy flux is measured in watts per square meter, which breaks down into kilograms per second cubed. Strain, remember, has no units at all. It is a pure ratio. And frequency has units of 1/seconds. So the right-hand side of our relationship, frequency squared times strain squared, comes out with units of 1/second squared. That leaves us short. We need something extra in the equation, something with units of kilograms per second, to make both sides agree. This is precisely the kind of moment where physicists reach for what is called dimensional analysis, a technique that sounds almost too simple to be powerful, but has repeatedly led to some of the deepest insights in the history of the subject. The idea is straightforward. If you know roughly what physical ingredients should be involved in a phenomenon, you can often figure out how they must combine, just by making sure the units come out right, even before you have derived the full and complete equation from first principles. Since we are dealing with a gravitational wave, a ripple in spacetime racing outward through the vacuum of space at the speed of light, it makes sense that the constants involved should include the speed of light itself and Newton's gravitational constant. the number that sets the overall strength of gravity throughout the universe. And if you check the units of the combination formed by the speed of light cubed divided by Newton's gravitational constant, something remarkable happens. Those units work out to precisely kilograms per second, exactly the missing piece we needed. So, folding that combination into our earlier scaling relationship, we arrive at an expression for the energy flux of a gravitational wave, one that scales as the speed of light cubed divided by Newton's gravitational constant, multiplied by the frequency squared, multiplied by the peak strain squared. This captures the correct scaling of the physics, even though we have deliberately ignored small numerical factors that a full, rigorous derivation from general relativity would include. Factors that do not change the overall picture we are building tonight. We are actually interested in energy density, not energy flux. But converting between the two is simple, since the wave is traveling at the speed of light. Energy density is just the flux divided by the speed of light. Dividing through, our expression becomes the speed of light squared, divided by Newton's gravitational constant, multiplied by frequency squared, multiplied by peak strain squared. This is the energy density carried by the gravitational wave itself, derived entirely from the physics of general relativity, independent of anything we said earlier about elastic rods or steel bars. Now we have two separate expressions for the same physical quantity, energy density, arrived at from two completely different directions. From the elastic materials side, we had 1/2 the effective Young's modulus multiplied by the peak strain squared. From the gravitational wave side, we now have the speed of light squared over Newton's constant multiplied by frequency squared multiplied by peak strain squared. If space-time really did behave in this narrow and specific sense like an elastic material carrying the same energy for the same strain, then these two expressions must be equal to one another. And when we set them equal and solve for the effective Young's modulus, something quietly beautiful happens. The peak strain appears on both sides of the equation and it cancels out completely. This is worth pausing on because it tells us something genuinely surprising. The effective stiffness of space-time in this model does not depend at all on how large the gravitational wave actually is. It does not matter whether the wave is faint or enormous, whether it barely nudges the detector or shakes it violently. The effective Young's modulus depends only on the frequency of the wave, nothing else. What remains, after the strain cancels away, is a clean expression, the speed of light squared, divided by Newton's gravitational constant, multiplied by the frequency squared. So let's put in real numbers, the same numbers that came out of that laboratory in Louisiana and that laboratory in Washington State on that quiet night in 2015. The gravitational wave detected by LIGO had a frequency of roughly 100 cycles per second, a note that would sit, if you could hear it, somewhere close to the lowest rumbling notes on a piano. Substitute that value in, along with the known values of the speed of light and Newton's gravitational constant, and the effective Young's modulus of spacetime comes out to approximately 1.3 times 10 to the 31st power pascals. Compare that to steel, sitting at around 10 to the 11th power pascals, and the ratio between the two comes out to almost exactly 10 to the 20th power. That is the number Rainer Weiss gave that night in the lecture hall, standing beside Kip Thorne, answering a question that sounded, at first, almost like a joke. Space, at the frequencies LIGO can detect, behaves as though it were roughly 100 billion times stiffer than steel. It is worth sitting with what that number actually means. because it is easy to let a phrase like 10 to the 20th power wash past you without really absorbing it. If you took every bridge, every skyscraper, every ship, every piece of steel infrastructure ever manufactured across the entire history of human civilization, and somehow combined all of their resistance to stretching into a single number, you would still fall unimaginably short of the effective stiffness spacetime displayed that night. And yet, despite that almost incomprehensible stiffness, the waves still managed to visibly, measurably stretch space by a tiny but real amount, because the collision that produced it was itself almost incomprehensibly violent, releasing more energy in a fraction of a second than every star in the visible universe combined, radiating outward not as light but as motion in the fabric of existence itself. So now we have arrived somewhere solid. We have a real, physically motivated way of assigning spacetime an effective stiffness, borrowed carefully and honestly from the mathematics of elastic materials, anchored to an actual measurement made by an actual instrument, confirming an actual prediction Einstein made almost a century earlier. And once you have a stiffness, a genuine resistance to deformation, a question begins to form in the back of your mind, one that feels almost forbidden to ask out loud. Every material that has a stiffness, every material physicists have ever studied in a laboratory, glass, steel, diamond, bone, concrete, also has a breaking point. Stretch any of them far enough, apply enough stress for long enough, and eventually the atomic bonds holding them together simply give way. Cracks form, cracks grow, and the material fails, sometimes gradually, sometimes catastrophically, all at once. If spacetime has something that behaves like a stiffness, does it also have something that behaves like a breaking point? Could the fabric of the universe itself, under the right extreme conditions, tear to even begin approaching that question honestly? We need to leave the world of gravitational waves for a moment and step into an entirely different corner of physics. The physics of fracture. The physics of why glass shatters, why metal fatigues, why bridges eventually fail. And we are going to discover that the man who first cracked that problem nearly a century ago was not thinking about the universe at all. He was thinking about cracks in ordinary glass, and he had no idea that his equations would ever be pointed at the sky. Part 5. The engineer who explained why things break. In the years following the First World War, a British aeronautical engineer named Alan Griffith found himself puzzling over a problem that had frustrated scientists and engineers for generations. Why do brittle materials, glass in particular, break at forces far weaker than you would expect from their underlying chemistry? If you calculated, from first principles, how strong the atomic bonds inside glass actually are, and worked out how much force it should theoretically take to pull those bonds apart, you would predict a material of extraordinary strength, one that should resist enormous stress before failing. And yet, in reality, glass breaks easily. A small scratch, a tiny imperfection invisible to the naked eye, and the entire pane shatters under a fraction of the force theory says it should withstand. Something was missing from the picture. Something was allowing failure to happen far earlier than the raw strength of the material's chemical bonds should permit. Griffith's insight, published in 1921, was as elegant as it was unsettling. He realized that the key to understanding fracture was not the bulk strength of the material at all, but the tiny, often microscopic cracks and flaws hidden within it. Every real material, no matter how carefully manufactured, contains defects, tiny voids, tiny irregularities, tiny cracks too small to see. And Griffith showed that it is these defects, not the material's underlying chemistry, that determine when and how it fails. Here is the essential idea, stripped down to its simplest form. Imagine pulling on a piece of glass that contains a microscopic crack somewhere inside it. As you pull and as that crack begins to grow, two competing physical effects happen simultaneously, locked in a kind of quiet, invisible tug-of-war. On one side, growing the crack costs energy. To extend a crack, you have to break atomic bonds and create new surface area where none existed before. Two fresh faces of material now exposed to open space instead of connected to each other. This costs energy, a specific, well-defined amount for every unit of new surface created, a quantity physicists call the surface energy. The larger the crack grows, the more new surface must be created, and the more energy that process demands. On the other side, growing the crack releases energy. The material surrounding the crack was already storing elastic energy, the same kind of stored energy we talked about earlier, built up as you pulled and stretched the material before the crack ever began to move. As the crack extends, some of that stored elastic energy is released, relaxed, freed from the surrounding material. These two effects, the cost of creating new surface and the release of stored elastic energy, compete directly against each other. If growing the crack costs more energy than it releases, the crack simply stops. It refuses to grow any further, and the material holds together, at least for now. But if extending the crack releases more energy than it costs, something dramatic happens. The crack becomes unstable. It grows on its own, feeding itself, accelerating, and the material fails, often catastrophically, often in a fraction of a second. Griffith worked out the precise mathematical balance point between these two competing effects, and derived an expression for the critical stress at which a brittle material will fracture. Setting aside the small numerical factors that depend on the exact geometry of the crack, the relationship comes out remarkably clean. The critical stress squared scales as the Young's modulus of the material, multiplied by its surface energy, divided by the length of the crack itself. It is worth pausing to feel how sensible this equation actually is, because every part of it matches something we would intuitively expect. A material with a higher surface energy, one where breaking atomic bonds costs more, is harder to fracture, and the equation reflects that directly. A stiffer material with a higher Young's modulus stores more elastic energy for a given amount of strain, and so it too becomes more resistant to fracture, exactly as the equation predicts. And then there is the crack length itself, and this is the part that should genuinely concern you, because it tells you that longer cracks are dangerous. The larger a crack already is, the smaller the additional stress required to make it grow further and eventually, catastrophically, to make it grow without limit. This single insight that flaws and imperfections, not raw material strength, govern when things break, transformed engineering. It is the reason aircraft wings are inspected obsessively for the tiniest hairline cracks. It is the reason bridges are monitored for microscopic fatigue damage invisible to a casual glance. No material, no matter how strong its underlying chemistry, is ever perfectly free of defects, and Griffith's equation tells engineers exactly how dangerous a given defect actually is, long before it grows large enough to be seen with the naked eye. Now comes the conceptual leap. The moment where 100-year-old idea about cracked glass gets pointed, quite deliberately, at the fabric of the universe itself. What happens if we take Griffith's equation, built entirely to describe brittle materials like glass and ceramics, and simply apply it to spacetime, treating it purely as a thought experiment, as though it were a brittle fabric that could crack and tear the same way a window pane does? This is not, it must be said clearly, an established or mainstream area of physics research. It is a speculative, deliberately playful extension of two well-tested ideas, gravitational wave physics and fracture mechanics, pushed together to see where the mathematics leads. But it leads somewhere genuinely fascinating, because it forces us to confront three very specific questions, each one demanding an answer before we can move forward. First, what value should we use for the Young's modulus in Griffith's equation, when the material in question is not glass or steel, but empty space itself? Second, what value should we use for the crack length, the size of the flaw whose growth determines whether the material holds together or fails catastrophically? And third, and hardest of all, what value should we use for the surface energy, the cost of creating new surface area when a crack grows, when there is no atomic lattice, no chemical bond, no physical surface in any ordinary sense to speak of? The first question, at least, we have already answered. We spent the last several parts of tonight's journey carefully deriving an effective Young's modulus for spacetime, built directly from real gravitational wave data, anchored to an actual measurement made at LIGO. We can carry that value forward directly into Griffith's fracture equation. The second question points us toward one of the strangest and most fundamental scales in all of physics, a length so small that ordinary geometry itself is expected to lose meaning at distances shorter than it. In any real material, the crack length in Griffith's equation is ultimately limited by the material's microscopic structure, the spacing between atoms, the size of the crystal lattice, the point below which the idea of a smooth, continuous solid simply stops making sense. Below that scale, you are not looking at a deformed material anymore. You are looking at individual atoms, and the entire framework of continuous elasticity breaks down. Spacetime, as far as general relativity is concerned, has no known microscopic structure of that kind. But physicists do believe there is a length scale below which our smooth, continuous description of space is expected to fail. A scale where quantum effects and gravitational effects become so tightly intertwined that Einstein's elegant geometric picture of spacetime simply cannot be trusted anymore. That scale is called the Planck length, and it is almost unimaginably small. Roughly 10 to the minus 35th power meters, a distance so far beneath the size of an atom, so far beneath even the size of a proton, that comparing it to anything in ordinary human experience borders on meaningless. By choosing this smallest possible physically meaningful length as our crack length, we are deliberately constructing the most extreme, most favourable scenario for fracture that the mathematics can produce, an estimate for the maximum possible fracture stress this model could ever predict. The third question, the value of the surface energy of space-time itself, is where things become genuinely uncertain, genuinely speculative, and genuinely fascinating all at once. Because unlike the Young's modulus, which we derived from real measured data, there is no experiment anywhere that tells us how much energy it would cost to tear open a new surface in the fabric of space. We do not know that number. Nobody does. And so, rather than trying to calculate the critical fracture stress directly, we are going to have to approach the problem from an entirely different angle, asking instead how much energy could possibly be crammed into the smallest meaningful patch of space the universe allows before the geometry of that space itself is forced to respond. Part 6. The smallest cube in existence. To move forward, we need to ask a slightly different question than the one we started with. Instead of trying to calculate the exact fracture stress of space-time directly, which would require knowing a surface energy nobody has ever measured, we are going to ask something more tractable. How much elastic energy would be stored inside a single cube of space, 1 Planck length on each side, the smallest physically meaningful cube the laws of physics allow us to describe, at the precise instant that cube reaches the point of fracture? To answer that, we return once more to our earlier expression for elastic energy density, the amount of energy stored per unit volume of a stretched material. We had shown that this quantity is equal to 1/2 the stress multiplied by the strain. Using the definition of Young's modulus, we can rewrite that same expression in a slightly different but equivalent form, the stress squared divided by twice the Young's modulus. The volume of our tiny cube is simple to write down. Since each side has a length equal to the Planck length, the volume is just the Planck length cubed. Multiplying our energy density expression by this volume gives us the total elastic energy stored inside the cube, expressed in terms of stress, Young's modulus, and the Planck length. Now, we are specifically interested in the moment just before fracture begins. The instant the stress inside the cube reaches its critical value, the threshold at which Griffith's competing energies, the cost of creating new surface, and the release of stored elastic energy tip decisively toward failure. At that instant, we can substitute in Griffith's own expression for the critical stress, the one we derived earlier, where the critical stress squared scales as the Young's modulus multiplied by the surface energy divided by the crack length. And since we have already decided to use the Planck length as our crack length, this substitution flows through naturally. When we carry this substitution through the algebra, something genuinely elegant happens. The kind of moment in physics where a complicated tangle of variables suddenly collapses down into something clean and simple. The Young's modulus, which appears in the numerator from the critical stress expression and also in the denominator from the original energy density expression, cancels out completely. What remains, after everything else falls away, is a strikingly simple result. The elastic energy stored in the cube at the onset of fracture is roughly equal to the surface energy multiplied by the Planck length squared. It is worth pausing on how clean this result actually is. The stiffness of space, that almost incomprehensible number we spent the earlier parts of tonight painstakingly deriving from real gravitational wave data, has completely vanished from the equation. At first glance, that might feel like a disappointment after all that work. But it actually makes deep physical sense once you think it through. A stiffer material for a given strain stores more energy, yes, but that same stiffness also demands a higher stress before a crack will grow, which pushes the fracture threshold higher too. These two effects, stiffness storing more energy and stiffness resisting crack growth, work in exactly opposite directions, and at the critical point of fracture, they cancel each other out perfectly. What survives is simply the surface energy multiplied by the area of one face of our tiny Planck scale cube, the Planck length squared. Physically, this result says something quietly beautiful. The energy needed to break open the smallest meaningful patch of space is simply whatever it costs, per unit area, to create the two new surfaces that fracture would produce, multiplied by the area of that patch. Everything else, all the complicated machinery of stiffness and stress, has been stripped away, leaving behind the purest, most essential version of the question. But we are still left with that one unknown quantity haunting the equation, the surface energy of spacetime itself, a number nobody has ever measured, and that no experiment currently existing could ever hope to measure directly. Our equation alone cannot tell us its value. So instead, we are going to flip the entire question around. Rather than asking what the surface energy actually is, we are going to ask something we can actually answer. What is the absolute maximum amount of energy that could plausibly be concentrated into a region of space as small as a single Planck length before something else in the universe intervenes to stop it? And this is where the story takes its strangest, most conceptually vertiginous turn of the entire night, because the answer involves something almost nobody outside of theoretical physics has ever heard of: a maximum possible power, a fundamental speed limit not for velocity but for the rate at which energy itself can be delivered anywhere in the universe. Here is the reasoning that gets us there. If you try to concentrate too much energy into too small a region of space, something dramatic happens, something general relativity itself insists upon. The gravitational field generated by that concentrated energy becomes so intense that the region collapses in on itself, forming an event horizon, the boundary of a black hole. Space, in a very real sense, refuses to allow arbitrarily dense concentrations of energy to simply sit there peacefully. Push too much energy into too small a space, and the geometry of that space responds by curving in on itself entirely, sealing that energy behind a horizon from which nothing, not even light, can ever escape. This suggests there is a natural, physically motivated upper limit to how much energy can be crammed into a region the size of a single Planck length before gravitational collapse takes over. And remarkably, using nothing more than dimensional analysis, the same simple technique that gave us the effective stiffness of spacetime earlier tonight, physicists can estimate this limit directly. The starting point is the idea of a maximum possible power, sometimes called the Planck power, or occasionally discussed in the literature as an absolute upper bound on luminosity, the rate at which any physical process anywhere in the universe could ever emit energy. Using the speed of light and Newton's gravitational constant combined in the specific way that produces units of power. Energy per unit time, this maximum power scale comes out to the speed of light raised to the fifth power divided by Newton's gravitational constant. Numerically, this comes out to an almost incomprehensible value, somewhere in the neighborhood of 10 to the 52nd power watts. To offer some sense of scale, the total power output of every star in the observable universe combined, all of them, radiating simultaneously across the entire visible cosmos, falls dramatically short of this theoretical limit. This is not a power output any physical process we know of has ever come close to reaching. It represents something closer to an absolute ceiling, a scale beyond which the very geometry of spacetime is thought to intervene. But power alone does not give us an energy. Power tells us a rate, energy delivered per unit time. To convert that into an actual total energy, we need to know for how long this maximum power could plausibly act on the tiny scale we are interested in. And the natural, physically motivated answer is the time it takes light itself to cross a single Planck length, the smallest physically meaningful unit of time the universe allows, known as the Planck time. Since time is simply distance divided by speed, the Planck time works out to the Planck length divided by the speed of light. Numerically, this comes out to something almost too small to comprehend, roughly 10 to the minus 44th power seconds, a duration so brief that comparing it to anything in ordinary experience, the blink of an eye, the vibration of an atom, the decay of the shortest-lived subatomic particles feels almost meaningless. It is simply unimaginably brief. Multiplying the maximum possible power by this shortest possible duration of time gives us the maximum energy that could plausibly be delivered into a Planck-sized region of space during a burst lasting 1 Planck time. This quantity, built entirely from the speed of light and Newton's gravitational constant, is known as the Planck energy, and it represents one of the most fundamental natural scales in all of theoretical physics, a scale that appears again and again in completely different contexts whenever physicists probe the deepest, smallest structure the universe is thought to possess. We now have everything we need to construct the central inequality of tonight's entire investigation, the mathematical statement that will finally let us ask, with real numbers behind it, whether space-time itself could ever actually break. Part 7. The force that holds the universe together. We have now arrived at the point where two entirely separate lines of reasoning are finally ready to meet. On one side, we have the elastic energy stored inside a single Planck scale cube of space at the precise instant it reaches its fracture point, an expression built from the unknown surface energy multiplied by the Planck length squared. On the other side, we have the Planck energy itself, the maximum amount of energy that could plausibly be delivered into a region that small, in a burst lasting no longer than the shortest physically meaningful interval of time, before the very geometry of space intervenes and collapses that energy into a black hole. For space-time to actually break, for a crack to genuinely form and grow, the energy available must be at least as large as the elastic energy required to trigger fracture. If the available energy falls short, the crack simply cannot form, no matter how favourable the other conditions might be. This gives us a clean, physically meaningful condition, a fracture inequality. The maximum energy available must be greater than or equal to the elastic energy stored at the onset of fracture. Substituting in both of our carefully derived expressions and simplifying the resulting relationship produces something worth sitting with for a long moment, because it is, in a real sense, the heart of everything we have built tonight. It is worth pausing here to look closely at the units involved, because they reveal something the equation itself does not immediately make obvious. The surface energy has units of joules per square meter, energy per unit area. The Planck length has units of meters. Multiply the two together, and the units that emerge are joules per meter, which, if you think back to the very basic definition of force, energy divided by distance, turns out to be exactly equivalent to newtons, the ordinary unit of force. In other words, this combination, surface energy multiplied by Planck length, is not just an abstract mathematical quantity. It is, quite literally, a force. Specifically, it represents the characteristic force associated with tearing open a single Planck-sized patch of spacetime, if spacetime possessed anything resembling a surface energy in the first place. And the inequality we derived tells us something remarkably specific about that force. It cannot exceed a particular combination of fundamental constants, the speed of light raised to the fourth power, divided by Newton's gravitational constant. This combination already has a name in theoretical physics. It is called the Planck force, and it carries a numerical value of roughly 10 to the 44th power newtons. A force so enormous that comparing it to anything in ordinary human experience feels almost absurd. It dwarfs the combined gravitational pull of every star, every planet, every black hole in the observable universe, acting all at once. The Planck force is not some obscure arbitrary number pulled out of thin air for the sake of this thought experiment. It connects directly to a genuinely serious idea within theoretical physics, sometimes called the maximum force conjecture, or occasionally the maximum tension principle. The core suggestion, explored seriously by several theoretical physicists over the past few decades, is that classical, general relativity may simply refuse to permit any force or tension in the universe to exceed this specific value. Just as special relativity forbids anything from exceeding the speed of light, general relativity may impose an analogous, equally absolute limit on force itself. The reasoning behind this conjecture echoes something we have already encountered tonight. Attempts to concentrate too much force, too much energy, into too small a region inevitably run headlong into gravitational collapse. Push hard enough, concentrate enough energy densely enough, and instead of tearing space apart, you simply create a black hole. The geometry of space-time itself steps in, almost protectively, and prevents the extreme concentration of force or energy that would otherwise be required to break it. So here is how we can finally read our central inequality. Now that all the pieces are assembled, if we define the quantity surface energy multiplied by Planck length as the characteristic tearing force associated with breaking open a single Planck-sized patch of spacetime, then that tearing force must never exceed the Planck force if fracture is to remain even energetically conceivable within this framework. But it is critically important to be honest about exactly what this inequality does, and does not tell us. It gives us an upper bound, a ceiling, a maximum possible value. It does not tell us the actual tearing force of spacetime, whatever that might genuinely mean. It does not tell us how close to this limit the real universe actually sits, or how many orders of magnitude below it we might safely, comfortably remain. The true tearing force of space, whatever physical reality that phrase might correspond to, could sit anywhere beneath this ceiling, and our reasoning gives us no way of pinning down exactly where. What we can do, however, is consider the single most extreme case the mathematics allows, the scenario in which this bound is fully saturated, where the tearing force sits at exactly the Planck force, the absolute maximum the framework permits. This represents the most generous, most fracture-friendly scenario imaginable within this entire model, and even here, the numbers we are about to calculate remain almost impossible to comprehend. If we set the tearing force equal to the Planck force exactly, and rearrange to solve for the surface energy this would require, we arrive at a truly staggering number. Substituting in the known values of the speed of light, Newton's gravitational constant, and the Planck length, we find a maximum possible surface energy of roughly 10 to the 79th power joules per square meter. It is worth taking a long, slow moment to feel the scale of that number, because it is genuinely almost impossible to hold in your mind honestly. For comparison, the surface energy of ordinary glass, the actual physical cost of creating new surface area when a window pane cracks and shatters, is only a few joules per square meter. Most metals sit in a similarly modest range, somewhere between 1 and 10 joules per square meter. The theoretical maximum surface energy of space-time itself, in this most extreme, most fracture-friendly scenario we could construct, comes out roughly 80 orders of magnitude larger than that. A 1 followed by 79 zeros, standing in place of a number closer to 1 or 2. This tells us something profound, even if it cannot tell us everything we might wish to know. It does not prove that space-time is unbreakable in some absolute final sense. What it tells us is that if the fracture analogy carries any real physical meaning whatsoever, then the natural, physically motivated scale for any such tearing force is the Planck force, an almost inconceivably enormous quantity, and the natural scale for the corresponding surface energy is correspondingly almost unimaginably large. If space-time can be torn at all, The extreme limiting case within this framework corresponds to a fabric of reality that is resistant to tearing on a scale that dwarfs anything we have ever measured, tested, or even seriously imagined for any ordinary material. But there remains one final thread left dangling in this entire investigation. One last question we have not yet allowed ourselves to ask. We now have two very different numbers describing spacetime, arrived at through two very different chains of reasoning. From the elastic, gravitational wave side of our investigation, we derived an effective Young's modulus for spacetime, a genuine stiffness, anchored to real data collected on that quiet night in 2015. From the fracture, Griffith-inspired side of our investigation, we derived a hypothetical maximum surface energy, a genuine breaking threshold, anchored to the Planck scale and the maximum force conjecture. Is there any way to connect these two numbers directly to one another? Is there some frequency, some specific rate of oscillation at which the stiffness we measured with LIGO and the fracture threshold we derived from Griffith's century-old equations actually become comparable to one another? And if such a frequency exists, what would it actually represent, physically, about the true limits of spacetime itself? Part 8. Where the two numbers finally meet. At first glance, the two quantities we have derived tonight do not seem like they should be comparable at all. The effective Young's modulus of spacetime has units of pascals, which, as we established earlier, break down into joules per cubic meter and energy per unit volume. The surface energy of spacetime, by contrast, has units of joules per square meter and energy per unit area. One describes how energy is packed into a volume of space. The other describes how energy is packed into a surface. They are not, on the face of it, the same kind of thing at all, and you cannot simply set one equal to the other and expect the units to agree. But there is a way to bridge that gap, and it involves nothing more exotic than a single length. If you take an energy density, an energy per unit volume, and multiply it by a length, the units work out cleanly to an energy per unit area, exactly matching a surface energy. Physically, this makes sense too. You are essentially taking the amount of energy packed into a small volume and asking what that amount becomes if you concentrate it instead onto a flat surface with a thickness equal to that chosen length. And because we are already working at the very edge of what physics can meaningfully describe, the natural length to use here is once again the Planck length, the same smallest possible meaningful distance that has quietly anchored almost every calculation tonight. If we multiply our effective Young's modulus by the Planck length, we obtain a genuine energy per unit area, a quantity we can now legitimately compare side by side with the hypothetical maximum surface energy we derived from the fracture side of our reasoning. Recall that our effective Young's modulus, derived from gravitational wave physics, took the form of the speed of light squared, divided by Newton's gravitational constant, multiplied by the frequency of the wave squared. Multiplying this entire expression by the Planck length gives us a new quantity, one that depends explicitly on frequency, and we can now ask a very specific, very pointed question. At what frequency does this quantity, built from the stiffness of space as measured through gravitational waves, become comparable to the maximum surface energy scale we derived from Griffith's fracture equation, pushed all the way to the Planck scale? To answer that, we simply rearrange our expression to solve for frequency directly. Working through the algebra carefully, the frequency comes out proportional to the square root of the surface energy multiplied by Newton's gravitational constant, divided by the speed of light squared, all divided once more by the Planck length. Now we substitute in the maximum surface energy value we derived earlier, that almost inconceivable number, roughly 10 to the 79th power joules per square meter, representing the most extreme, most fracture-friendly scenario the maximum force conjecture allows. When we carry this substitution through and simplify the resulting expression fully, something remarkable happens. Nearly everything cancels, and what remains is astonishingly clean: the speed of light, simply divided by the Planck length. If you recall, several parts ago, we defined the Planck time as the Planck length divided by the speed of light, the time it takes light itself to cross the smallest physically meaningful distance the universe permits. And the expression we have just arrived at, the speed of light divided by the Planck length, is nothing more than the reciprocal of that quantity, 1 divided by the Planck time. This specific combination already has a name in physics. It is called the Planck frequency, and it carries a value of roughly 10 to the 43rd power hertz. So here, finally, is the answer to the question that has been quietly building across this entire investigation. When does the effective stiffness of space-time, the quantity we derived directly from real gravitational wave data collected at LIGO, become comparable to the theoretical maximum surface energy required for fracture, the quantity we derived from Griffith's century-old equations for cracking glass, pushed to their absolute limit? The answer is that these two numbers only become comparable at a frequency of oscillation equal to the Planck frequency itself, roughly 10 to the 43rd power cycles per second. It is almost impossible to convey how far beyond ordinary physics that frequency actually sits. The gravitational wave detected by LIGO in 2015, the wave that stretched a 4-kilometer tunnel by less than the width of a proton, oscillated at roughly 100 cycles per second. The frequency at which our fracture model suggests space-time might genuinely begin to strain toward its breaking point is roughly 10 to the 43rd power cycles per second. That is not merely a large gap. It is a gap of 41 orders of magnitude, a difference so vast that comparing the two frequencies is almost like comparing the width of a single atom to the entire diameter of the observable universe, and then multiplying that comparison by itself several times over. Ordinary gravitational waves, the kind produced by colliding black holes, by merging neutron stars, by any astrophysical process we have ever observed or ever expect to observe with current or foreseeable technology, come nowhere remotely close to this scale. Even the most violent, most energetic events in the known universe, the most extreme collisions between the densest objects physics allows, produce gravitational waves that sit an almost unfathomable distance below the frequency at which our model suggests space-time itself might genuinely begin to feel strain approaching its theoretical limit. So, after everything, after the stiffness derived from real data, after Griffith's century-old equations for cracking glass, after the Planck force and the maximum force conjecture and the delicate cancellation of variables that led us here, what is the honest answer to the question this entire night has been built around? Can space-time actually break? The honest answer, the answer any careful physicist would insist upon, is that we do not know. And it is worth being completely clear about why we do not know, because the reason itself is illuminating. General relativity, Einstein's theory, the same theory that predicted gravitational waves nearly a century before we built instruments sensitive enough to detect them, does not describe space-time as a brittle material. It contains no atoms. It contains no chemical bonds. It contains no crystal lattice. no microscopic structure of any kind that a real material would possess. There is no literal Young's modulus written into Einstein's equations, no literal surface energy waiting to be measured in some future experiment. Everything we have done tonight, every equation, every derivation, every number, has been a carefully constructed analogy, a way of borrowing language and mathematics from one branch of physics and applying it deliberately and speculatively to a completely different one. But it is a revealing analogy, precisely because of where it leads. When you push this borrowed framework as far as it can honestly go, when you follow the mathematics from gravitational waves through Griffith's fracture theory, through the Planck force and the maximum force conjecture, all the way to its logical conclusion, the different threads of reasoning do not diverge into nonsense. They converge, cleanly and consistently, at exactly the same place. The Planck scale. The smallest length, the shortest time, the highest frequency that physics, as we currently understand it, is even equipped to describe. And that convergence is not nothing. It is, in fact, deeply significant. Because the Planck scale is not just some arbitrary number that happened to fall out of a speculative calculation. It is the very place where physicists already expect Einstein's smooth, continuous description of spacetime to require something deeper, something we do not yet possess. It is the boundary where general relativity and quantum mechanics, two of the most successful theories in the history of science, both begin to lose their grip on reality, unable to agree with each other about what is actually happening. It is the edge of the map, the place where our best equations, however brilliant, however thoroughly tested, quietly stop being reliable guides. So if spacetime can break, this entire framework suggests we do not yet know what that breaking would actually mean physically. We do not know what would emerge on the other side of such a fracture, whether it would even resemble anything we could call space at all. But this speculative, admittedly playful argument suggests, with surprising consistency, exactly where we might need to look for an answer. Part 9. The place where two theories refuse to agree. To understand why the Planck scale keeps appearing at the end of every path we have followed tonight, we have to step back and confront something uncomfortable about modern physics, something that rarely gets said plainly in classrooms, but that every working physicist knows intimately. We do not actually have one single theory of the universe. We have two, and they do not agree with each other. General relativity, Einstein's theory of gravity, describes the universe on the largest scales imaginable. It tells us how planets orbit stars, how stars orbit galaxies, how galaxies bend the light of everything behind them, how black holes form, how the universe itself has been expanding since its earliest moments. It describes gravity not as a force reaching out across empty space, but as the curvature of space-time itself, a smooth, continuous geometric fabric that bends in response to mass and energy, and in turn tells mass and energy how to move. It is, by any reasonable measure, one of the most successful theories human beings have ever constructed. It predicted gravitational waves nearly a century before we built anything capable of detecting them, and when we finally did, in 2015, the signal matched Einstein's predictions with breathtaking precision. Quantum mechanics, meanwhile, describes the universe on the smallest scales imaginable. It tells us how electrons behave inside atoms, how photons carry energy, how particles can exist in strange, ghostly superpositions of multiple states at once, only settling into a single definite outcome the moment they are measured. It, too, is extraordinarily successful, arguably the most precisely tested theory in the history of science. correctly predicting the outcomes of experiments to more decimal places than almost any other framework physicists have ever produced. The trouble is that these two theories are built on fundamentally different, almost philosophically opposed, foundations. General relativity treats spacetime as smooth and continuous, a geometric surface that can be divided infinitely finely, with no smallest possible unit of distance or time built into its mathematics. Quantum mechanics, by contrast, is a theory built entirely around discreteness, around the idea that certain physical quantities do not vary smoothly and continuously at all, but instead jump between fixed, quantized values, with nothing meaningful existing in between. For most everyday purposes, this disagreement simply does not matter. When physicists calculate the orbit of a planet, they use general relativity, and quantum effects are so vanishingly small they can be entirely ignored. When physicists calculate the behavior of an electron inside an atom, they use quantum mechanics, and the curvature of space-time around something as small and light as an electron is so utterly negligible it might as well not exist. The two theories peacefully occupy entirely separate domains, general relativity ruling the very large, quantum mechanics ruling the very small, and in the vast, comfortable middle ground where most of physics actually happens, both theories work beautifully, and nobody has ever needed to ask them to cooperate directly. But there are places in the universe where this comfortable separation breaks down completely. Places where something is simultaneously so massive that its gravity cannot be ignored, and so small that quantum effects cannot be ignored either. The center of a black hole is one such place, a region where an enormous amount of mass has been crushed down into a volume so small that general relativity predicts a singularity, a point of infinite density where its own equations simply stop producing meaningful answers. The first fraction of a second after the beginning of the universe is another such place, a moment when the entire observable cosmos was compressed into a region small enough that quantum effects should have dominated everything, and yet dense enough that gravity should have been overwhelmingly powerful too. And the Planck scale, the length, time, and energy scale that kept emerging again and again throughout tonight's entire investigation is the theoretical boundary at which this tension becomes completely unavoidable. At distances shorter than the Planck length, at times briefer than the Planck time, at energies exceeding the Planck energy, both quantum effects and gravitational effects become significant simultaneously. And neither general relativity nor quantum mechanics, on their own, can be trusted to describe what is actually happening. This is precisely why our investigation tonight, built from an admittedly speculative analogy between spacetime and a brittle material, kept converging on that exact same scale, no matter which path we followed to get there. The gravitational wave side of our reasoning gave us an effective stiffness for space, built entirely from general relativity. The fracture side of our reasoning, borrowing Griffith's century-old equations, forced us to choose a smallest meaningful crack length, and the only physically motivated choice available was the Planck length, a quantity that only makes sense once you start taking quantum gravity seriously. Every thread we pulled on tonight led back to the same boundary, the same edge of the map, the exact place where physicists already suspect our current theories must eventually give way to something deeper. Physicists have spent decades searching for that deeper theory, a framework capable of unifying general relativity and quantum mechanics into a single, internally consistent description of reality, often called a theory of quantum gravity. Several serious candidates exist. String theory proposes that the fundamental building blocks of the universe are not point-like particles at all, but tiny vibrating strands of energy, with different vibration patterns corresponding to different particles, and with gravity emerging naturally as one of the theory's necessary consequences. Loop quantum gravity proposes something even stranger, that space itself is not smooth and continuous at all, but granular, built from discrete, indivisible units at the Planck scale, the way a photograph that looks smooth from a distance dissolves into individual pixels the closer you look. Neither theory has been experimentally confirmed. Neither has produced a prediction that current technology could actually test, because the energies and scales involved sit so far beyond anything any particle accelerator on Earth could ever hope to reach. That direct experimental verification remains, for now, essentially out of reach. And this is precisely the frustration and the fascination that our investigation tonight has been quietly circling the entire time. We have built a careful, mathematically consistent argument suggesting that if space-time has anything resembling a breaking point, that breaking point sits at the Planck scale. And the Planck scale is exactly the place where we do not yet have a reliable theory capable of telling us what breaking would even mean. Would a fracture in space-time look like a literal tear, a discontinuity, where the smooth geometry of general relativity simply stops making sense? Would it instead reveal the discrete, granular structure that loop quantum gravity predicts lies hidden beneath the smooth surface we experience at ordinary scales, the pixels beneath the photograph? Would it connect, somehow, to the extra dimensions and vibrating strings proposed by string theory? Nobody currently knows, and it is entirely possible that nobody will know for a very long time, because the experimental tools required to probe physics at the Planck scale directly remain, for now, firmly in the realm of science fiction rather than laboratory reality. But there is something worth holding on to here. Something that should feel less like a disappointment and more like a kind of quiet reassurance. The fact that our speculative fracture model, built from nothing more than gravitational wave data and a century-old theory of cracking glass, converges so cleanly on the exact scale where physicists already expect new physics to emerge is not a coincidence born of sloppy reasoning. It is a sign that the underlying logic, however playful in its construction, is tracking something real about the structure of the universe. It is pointing with genuine consistency toward the same boundary that every other serious approach to quantum gravity has independently identified as the place where our current understanding of reality runs out. Part 10. What a fracture might actually look like. If we allow ourselves, just for a moment, to take this analogy seriously enough to ask what a fracture in space-time might actually resemble, we have to be honest about the fact that we are now standing at the very edge of speculation, in territory where physicists themselves disagree, and where no experiment currently exists to settle the question. But speculation grounded in real mathematics is still worth exploring, because it forces us to confront just how strange the answer might turn out to be, whatever it eventually is. Start with the most conservative possibility, the one that requires bending our existing theories the least. Perhaps a fracture in space-time, if such a thing is even meaningful, would not look like a tear at all, in the everyday sense of that word. When glass breaks, or steel snaps, or rock splits, the material separates into pieces, with genuine empty space opening up between what used to be a single connected object. But space-time is not a material sitting inside some larger container of empty space. Space-time is what defines the very concept of distance, of separation, of here versus there. There is no larger stage for a broken piece of space-time to fall away into. If space-time tears, there may be no meaningful sense in which the two sides of that tear move apart from each other. because the concept of moving apart already presupposes the existence of the space-time that would be doing the tearing. This is part of why physicists who take the maximum force conjecture seriously often frame the Planck force less as a literal breaking point, and more as a kind of cosmic censorship, a built-in safety mechanism woven into the very geometry of general relativity. Recall that attempts to concentrate too much energy into too small a region do not simply strain the fabric of space until it gives way. Instead, they trigger gravitational collapse, forming an event horizon, a one-way boundary beyond which nothing, not even light, can ever return. In this picture, the universe does not allow space-time to be torn open by brute force, because long before you could ever apply enough stress to reach a genuine fracture point, the concentrated energy required to apply that stress would already have collapsed into a black hole, sealing itself away behind a horizon before the fracture could ever occur. The universe, in a sense, protects itself, not by making space-time infinitely strong, but by making it impossible to apply enough force in a small enough space without something else happening first. If this picture is correct, then space breaking and a black hole forming might not be two separate competing outcomes at all. They might be, in some deep and currently poorly understood sense, the very same event viewed from two different angles. The singularity at the center of a black hole, that point where general relativity's equations already predict infinite density and a complete breakdown of ordinary geometry, might already be exactly the kind of fracture our entire investigation tonight has been circling, hiding in plain sight inside every black hole that has ever formed, shielded from the rest of the universe by an event horizon that ensures we can never observe it directly and never will. There is something almost poetic in that possibility if it turns out to be true. It would mean that space-time has, in a sense, already broken countless times throughout the history of the universe. Every single time a massive star has collapsed at the end of its life, every time two neutron stars have spiraled together and merged, every time enough mass has been concentrated into a small enough region for gravity to overwhelm every other force in nature. It would mean that the fractures we have been speculating about tonight are not a distant hypothetical, confined to some far future experiment we cannot yet imagine building. They may already be scattered throughout the cosmos, at the centers of galaxies, at the remnants of dead stars, each one hidden forever behind a horizon that guarantees we will never see what actually happens at the moment space-time itself gives way. There is a second possibility, stranger still, that some theoretical physicists take seriously, though it remains firmly in the realm of speculation rather than established science. Perhaps a fracture in space-time would not simply destroy space at that location, but would instead reveal what lies beneath it, the discrete. Granular structure that theories like loop quantum gravity predict is hidden underneath the smooth surface we experience at every scale our instruments can currently probe. In this picture, ordinary space-time, the smooth, continuous fabric Einstein described, would be something like the surface of a calm lake, appearing perfectly smooth from a distance, but actually made of individual, discrete molecules once you look closely enough. Under normal conditions, at ordinary energies and ordinary scales, this underlying graininess is completely invisible, smoothed out into the elegant, continuous geometry that general relativity describes so successfully. But push space-time hard enough, concentrate enough energy into a small enough region, and perhaps that smooth approximation simply stops holding, and the underlying discreteness becomes, for a fleeting instant, directly relevant to what happens next. If this second picture were correct, breaking spacetime would not mean destroying it in any absolute sense. It would mean exposing its true underlying nature, the pixels beneath the photograph, the discrete structure beneath the smooth illusion. What we currently call empty space, the seemingly featureless void stretching between every star and every galaxy, might not be fundamental at all. It might be an emergent property, arising from something more basic underneath it, the way the smooth, continuous feel of water emerges from the collective behavior of countless individual molecules. Each one following its own simple rules, none of them individually resembling anything like a liquid at all. There is a third possibility as well, one that connects our entire investigation back to the very phenomenon that started this whole journey. Gravitational waves. If space-time genuinely does have something resembling a fracture threshold at the Planck frequency, an oscillation rate of roughly 10 to the 43rd power cycles per second, then perhaps the earliest moments of the universe, the almost inconceivably brief period immediately following the Big Bang, were the one and only time in the entire history of the cosmos when conditions anywhere close to that threshold were ever actually reached. In the earliest instance of cosmic history, temperatures and energy densities were so extreme that essentially every known law of physics was pushed to its absolute limit simultaneously. If space-time ever came close to its breaking point, if it ever genuinely strained toward whatever the Planck scale represents physically, it would have happened then. In that first unimaginably brief sliver of existence, long before atoms, long before light could travel freely, long before anything resembling the smooth, orderly universe we inhabit tonight had settled into place. Some theoretical physicists have speculated that this could leave a trace, a kind of scar, buried somewhere in the structure of the cosmos, potentially detectable. At least in principle, in an extremely faint background of primordial gravitational waves, ripples generated not by colliding black holes billions of years after the beginning, but by the universe's own birth, still crossing the cosmos today, fainter than anything LIGO has ever detected, potentially fainter than anything any instrument built with current technology could ever hope to measure. If such a background exists, and if it truly does encode information about conditions near the Planck scale, it would represent, in a very real sense, an echo of the single moment in cosmic history when space-time came closest to whatever its ultimate limit actually is. None of these three possibilities can currently be confirmed. None of them can currently be ruled out either. They remain honest, mathematically motivated speculation, built from real physics pushed as far as it can currently go, standing at the exact boundary where our best theories quietly admit they no longer know what comes next. Part 11. Living inside the answer we do not have. There is something worth sitting with, quietly, before we bring tonight's journey toward its close. We began with a measurement, a real one, a gravitational wave produced by two black holes colliding more than 1 billion years ago, crossing the entire observable universe, arriving at a set of mirrors on Earth, and stretching a 4-kilometer tunnel by less than the width of a single proton. That measurement was not speculation. It was not a thought experiment. It happened, it was recorded, and it earned 3 physicists a Nobel Prize. Everything that followed, the effective stiffness of space-time, 10 to the 20th power times stiffer than steel, Griffith's century-old equations for cracking glass. The Planck force, the maximum force conjecture, the surface energy of space itself, was something different. It was an extended, carefully reasoned, mathematically consistent act of imagination, built entirely from real physics, but reaching, deliberately, into territory no experiment has ever confirmed, and no experiment currently under construction anywhere on Earth is likely to confirm any time soon. And yet, there is something quietly remarkable about where that imagination led. We did not simply invent a number and call it the breaking point of the universe. We built two completely independent chains of reasoning, one rooted in the physics of gravitational waves, one rooted in the physics of fracture mechanics, and we let them run forward on their own terms, following the mathematics wherever it happened to lead. And when we finally asked where those two chains might meet, where the stiffness of space, measured from real data, might become comparable to a hypothetical breaking threshold, drawn from a completely different branch of physics entirely, the answer was not scattered randomly across some meaningless range of possibilities. It converged, cleanly and specifically, at the Planck scale. The exact same scale that quantum gravity researchers, working from an entirely different direction, using entirely different tools, have independently identified as the place where our current description of reality is expected to break down. That convergence does not prove that space-time can break. It does not prove that a Young's modulus or a surface energy are, in some deep and literal sense, real physical properties of the vacuum. It is entirely possible, perhaps even likely, that space-time is not the kind of thing that breaks at all, that the entire concept of fracture, borrowed from a world of atoms and chemical bonds and crystal lattices, simply does not apply to the geometric fabric that Einstein described. Real physicists, careful ones, would rightly caution against treating tonight's entire investigation as anything more than an elaborate, if genuinely illuminating, exercise in dimensional reasoning. But that caution should not diminish what has actually happened here, because there is a deeper lesson buried inside this entire investigation, one that has nothing to do with whether space-time can literally crack like a window pane, and everything to do with how physics actually makes progress at the very outer edges of what it currently understands. Throughout the history of science, some of the most productive questions have come not from certainty, but from precisely this kind of speculative reasoning, taking a well-understood idea from one domain and asking, quite seriously, what happens if we push it somewhere it was never originally designed to go. Einstein himself did something remarkably similar when he took Maxwell's equations for electricity and magnetism, equations that were never designed to describe gravity at all, and asked what would happen if the speed of light really was the same for every observer, no matter how they were moving. That question, pursued rigorously, mathematically, without flinching from wherever the logic led, eventually produced general relativity itself, the very theory that gave us gravitational waves, black holes, and the expanding universe. Nobody knew, when Einstein began asking that question, whether it would lead anywhere useful at all. It could have been a dead end, an elegant piece of mathematics with no connection to physical reality. Instead, it became one of the most successful theories in the history of science, repeatedly confirmed by observation, right up to and including that quiet night in 2015, when a chirp lasting 0.2 of a second confirmed, nearly a century later, something Einstein had only dared to write down in the margins of his equations. Tonight's investigation into the possible breaking point of space-time sits in a much humbler category than that. It is not a new theory of physics. It is not a prediction that observatories anywhere in the world are currently racing to test. It is, honestly, closer to a thought experiment, a way of taking two well-established, thoroughly tested branches of physics, gravitational wave astronomy and fracture mechanics, and asking what happens when you let them speak to each other, using nothing more sophisticated than careful bookkeeping of units and orders of magnitude. And yet, even a thought experiment like this one earns its place because of where it points. It points, with remarkable consistency, toward the Planck scale, toward the deep, unresolved tension between general relativity and quantum mechanics, toward the single greatest unsolved problem remaining in fundamental physics. It reminds us that even in a universe where we have directly detected ripples in the fabric of existence itself, where we have measured distances thousands of times smaller than a single proton, where we have confirmed predictions made a century before the technology to test them even existed, there remains an entire regime of reality, the smallest, most extreme regime imaginable, that continues to sit almost entirely beyond our reach. Perhaps, someday, decades from now, or centuries from now, physicists will finally construct a working theory of quantum gravity, one that successfully unifies the smooth geometry of general relativity with the discrete, probabilistic strangeness of quantum mechanics. Perhaps that theory will tell us, with genuine precision, whether space-time truly has anything resembling a breaking point, and if it does, what actually happens the instant that point is reached. Perhaps it will reveal that our entire fracture analogy, however carefully constructed, was simply the wrong metaphor from the very beginning, and that the true answer looks nothing like cracking glass or snapping steel at all. Or perhaps it will reveal something closer to what we have speculated about tonight, that space-time does have a genuine limit, that black holes represent fractures we cannot see, hidden forever behind their own horizons, and that the earliest instant of the universe was the one and only moment in cosmic history when reality itself came close enough to that limit to feel the strain. We do not know which of these futures awaits. Nobody currently alive knows, and there is something worth genuinely appreciating in that uncertainty, rather than something to be uncomfortable about. It means the universe still has secrets. It means that even after a century of extraordinary progress, after confirming Einstein's wildest predictions with instruments sensitive enough to measure a change in distance smaller than a proton, there remains a frontier, close enough to touch with mathematics, still far enough away that no experiment can yet reach it. Part 12. The stillness above your head. Somewhere above you tonight, in the dark space between where you are lying and the ceiling of the room around you, space-time is doing exactly what it has always done, holding its shape, carrying you gently through the ordinary business of existing, without straining, without cracking, without any hint of the almost incomprehensible forces we have spent this entire night imagining pushed against it. And that stillness, that quiet, unremarkable, everyday stillness, is itself remarkable, once you understand what it is actually made of. You are resting inside a fabric so stiff that at the frequencies gravitational wave detectors can measure, it behaves as though it were roughly 100 billion times stiffer than steel. You are resting inside a fabric that, according to our best current theories, may carry a theoretical breaking threshold so extreme that reaching it would require concentrating energy into a space smaller than anything the human mind can genuinely picture, at a frequency so rapid that comparing it to anything you have ever experienced would be almost meaningless. And despite all of that almost unfathomable strength, the same fabric bent, gently and measurably, when two black holes collided over 1 billion years ago, sending a ripple across the entire universe that eventually reached a set of mirrors on Earth and told us, for the very first time, that space-time itself could move. There is something worth carrying with you as you drift toward sleep tonight in the fact that we were able to ask this question at all. Not so very long ago, in the span of human history, the very idea of measuring the stiffness of empty space would have sounded like nonsense, a question with no possible answer, asked in a universe with no possible way of answering it. And yet here we are, able to trace a single chirp of sound, lasting 0.2 of a second, all the way back through Einstein's century-old equations, through Griffith's theory of cracking glass, through the maximum force conjecture, through the Planck scale itself, to the very edge of what physics currently understands about the nature of reality. We did not find a final answer tonight. We found something perhaps more valuable than a final answer. We found the shape of the question, sharpened and refined, standing exactly at the boundary between everything we know and everything we do not yet know. We found that the universe, for all its almost unimaginable violence, black holes colliding, stars collapsing, the entire cosmos expanding outward from an almost inconceivably hot and dense beginning, still manages to hold itself together, gently, quietly, everywhere, all the time, without ever once, as far as we have ever been able to measure, actually tearing. Perhaps it never will. Perhaps space-time, whatever it truly is beneath the elegant mathematics Einstein gave us, is simply not the kind of thing that can break, the way glass breaks, or steel snaps, or rope frays and gives way. Perhaps the entire idea of fracture, borrowed so carefully tonight from the world of atoms and crystal lattices and surface energy, was always destined to remain a beautiful, useful, but ultimately imperfect metaphor, a ladder we climbed to see further, knowing all along we might eventually have to set it aside. Or perhaps, somewhere in the earliest, most violent instant of the universe's own birth, in a fraction of a second smaller than anything we have any real intuition for, space-time came closer to its limit than it ever has since, or ever will again, straining briefly toward a threshold it never quite crossed, leaving behind, perhaps, the faintest possible echo, still crossing the cosmos tonight, fainter than anything we have yet built the tools to hear. We do not know, and there is a kind of peace available in that not knowing, if you let yourself sit inside it for a moment. The universe is not finished revealing itself. Every question we manage to answer, every gravitational wave we detect, every equation we push a little further than it was originally meant to go, opens onto another question waiting patiently behind it. That is not a failure of physics. That is simply what it feels like to stand at the edge of genuine discovery rather than at the end of it. So let the ceiling above you stay exactly where it is tonight. Let the walls hold their shape, the way they have every night of your life, unremarkable, unbroken, unbothered by the almost unimaginable stiffness quietly built into the fabric surrounding them. Somewhere out there, more than 1 billion light years away, space-time is still rippling, faintly, from a collision that happened long before the Earth had ever formed, and that ripple is still crossing the universe tonight, growing fainter with every passing moment, carrying with it a question we have only just learned how to ask, and have not yet learned how to fully answer, drifting outward into a darkness that may or may not have a limit of its own. Somewhere out past the edge of what any telescope will ever see, that same ripple is still travelling, still crossing a universe it will never finish crossing. And you, lying here tonight, are held inside a fabric stiffer than anything human hands have ever built, and yet gentle enough that you have never once felt it strain. We asked tonight whether that fabric can break. We followed the mathematics as far as honest physics would let us go, and it led us, quietly, to the very edge of what anyone currently knows. That edge is not an ending, it is an invitation, the same invitation the universe has been offering curious minds for centuries. If tonight's journey gave your mind somewhere gentle to rest, let it carry you the rest of the way into sleep. And if you would like to stand at this edge again, subscribe so the next question is waiting for you when you wake. Sleep well. Spacetime is still holding.